Title of this lesson is Overview of Mutual Inductance and Transformers. So what we're going to do in this lesson and the next many lessons, many hours, is we're going to review the concept of inductance. That's what we've been talking about in circuits for almost from day one. And then we're going to continue on with the concept of mutual inductance. And then we're going to culminate in the concept of a transformer, which I know everybody watching this has heard of, so you know that transformers are important. But what we're going to do is, I could just start this lesson out by talking about the theory and the physics, and we are going to get into all of that stuff in the next section and beyond. But what I've decided to do in this lesson is to give you kind of a roadmap. That's why I call it an overview of mutual inductance and transformers. Because sometimes it gets a little bit difficult to see kind of where we're going. And so when we do the derivations later on, you might get a little bogged down in the math and the physics that we're going to do, which I personally find fascinating. But if I don't tell you the roadmap, you might get a little bogged down in some of the math that we're going to get into in the next couple of sections. So in order to avoid that, I really want you to have a bird's eye overview of where we are going. So in this lesson, there's going to be minimal math. We'll have a little bit of math. It'll mostly be an overview discussion reminding you what inductance is, what the concept of mutual inductance is without all of the heavy theory. And then we're going to get into the concept of a transformer, again, without all of the heavy theory. We'll do a quick little example at the end just to show you what a transformer is used for, so that you can understand where it comes from. But just keep in mind that once we finish this overview lesson, we're going to spend the next 5, 6, 7 hours diving into the theory behind every one of these concepts, the actual theory behind how we derive a lot of these equations. And we'll be getting into just so much detail, which you need to understand to be able to do practical work and solve problems. But this is an overview so that you can keep this in the back of your mind as we go through all of those lessons, so that you have that roadmap in mind and you know where we're going and you know how it fits together. So we're going to start with something I know everybody watching this has heard of and knows about. If you haven't, you can go back to my previous lessons. We're going to talk about the concept of an inductor, or let's call it self-inductance. You'll understand why in a second. We're going to call it self-inductance. Right? First thing you need to realize is that you might say, why is it called self-inductance? Well, reality, every inductor that we've ever talked about in this class has been self-inductance. We just didn't use that word because it was just inductor. We called it an inductor or inductance. But every inductor you've ever talked about or heard about has what's called self-inductance associated with it. And what I mean by that is an inductor, as you recall, is just a coil of wire, literally just a coil of wire, very tightly wound, with a certain number of turns associated with it. So we might say that this inductor has N turns. So literally, if I were winding an inductor in a coil, I might use this cylinder that I have here, this pin, as a form, and I might wind it with 25 turns. And then I can remove the center out. I don't need a center piece in there. I can just use it to make the shape. But I have that guy with so many turns. And then we say, if you remember, the way the sign convention goes, if you go back to the very first lesson on inductors, if we have current coming in here, and this could be driven by some source, any source of any kind. It could be just an AC source, a sinusoid, or something like that going into this guy. Then we say, and we've talked about, we never discussed the theory, but we said that there is a voltage drop that's going to come up here across this inductor when the current is changing. You know, we talked about that before a long time ago. I'm reminding you. If you have current going through that coil of wire and that current is fixed, if it's DC, if it doesn't change, then the voltage here, there is no voltage. It just disappears. It behaves like a short circuit, right? But when that current's going up and down, up and down, up and down, there exists a voltage that kind of pops up, for lack of a better word. It starts to arise. We'll discuss why in just a second. And that voltage, as you probably remember, or you should remember, is the following. The voltage in this direction, with this polarity when the current is going in that direction, is some parameter we call L, the inductance, times di dt. Now, you should all know what this means, but if you don't remember this di dt, it just means derivative. It means the voltage is proportional to the inductance. We call that L, right? But it's also proportional to how much the current is changing. Di dt obviously is how much the current's changing. So if you have current that's changing really fast, then the derivative is very high, so the voltage is high. If the current is changing very slowly, in other words, really slow changes in the current, then the derivative is smaller and the voltage is smaller. And if the current doesn't change at all, that means it's constant DC, then the derivative is 0, and so the voltage will be 0, which is exactly what I said in words would happen if there's no changing going on in the current. And then we said that this guy, this inductance here, the unit here is henries. Henries. And you can use millihenries and so on and so forth. So why is this going on is the basic idea. Now I'm not going to draw a bunch of magnetic field diagrams. I'm going to do that in the next section. But you can think of this current here. It's a fundamental fact of physics that when we have an electric current flowing, when charges are moving, there exists what we say is a magnetic field. It's an invisible field surrounding that current. I'm going to draw a lot of pictures of that field in the next section when we talk about the physics a little more. But you can think of it as a field that's kind of inside of this coil of wire, mostly anyway, due to the flow of the current. Now, when the current is changing, it means the magnetic field is getting bigger, smaller, because the field is proportional to the current. So if the field is going wah, 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 if the current is going up, down, like a sinusoid, then the field is literally getting stronger, weaker, stronger, weaker, stronger, weaker. And the voltage is basically proportional to when that magnetic field is changing. Cutting across is what we say, when it's cutting across through the coil of wire. So when the magnetic field cuts through, for lack of a better word, it's invisible, right? But still, you can envision those magnetic field lines cutting through that conductor there, that coil, and when the changing happens, the cutting through happens, a voltage arises. So that's why whenever the current is constant, we do have a magnetic field here, but it's a static field that's not changing, so there's no cutting through, for lack of a better word, through that coil, because it will be a static field if the current is fixed. We'll draw a lot of pictures of that in the next section. That's the idea here. Whenever we have a changing magnetic field cutting through that coil, we get a voltage here. Now that should more or less be a review of things that we talked about a long time ago when we introduced the concept of an inductor. Now let's talk about something else. Instead of self-inductance, we're going to talk a great length in this class, something called mutual inductance. Mutual inductance. And what that means is if you have, let's say, a coil here, an inductor, right? And it's driven by some source, whatever the source is, I don't care. I'm going to say it's a current source. Obviously, it's going up and down like a sinusoid. Then that means we have an inductor here. It has an inductance L and all that good stuff. Now this inductor, this number 1 inductor here, has N1 turns. We call it N1 because I'm going to draw another inductor in a second that'll have a different number of turns. So actually, to give me some room in the drawing here, let me write it like this, N1 turns, like this. Now, if I create another inductor and I move it physically close to the first one, like this, I'll leave this side open for now, but I'll just put a coil of wire physically very close to the initial coil, like this, and that second coil has what we call N2 turns. In other words, this coil might have 52 turns, and this coil might have 104 turns, or whatever, 25 and 30, or whatever. There could be different, is what I'm trying to say. The physical length of the coil and all that can be different along with the different number of turns involved, right? Then what we have is a current driving on this side, and let's say we want to measure the voltage drop on this side, V2. So what's going to happen in this case is this current source is going to drive a current through this inductor. This current is going to generate a magnetic field as a result of flowing through the inductor. And because it's sinusoidal, the magnetic field is going to be getting bigger, smaller through here. But since we've taken the second coil and we physically moved it very close to the first coil, then the magnetic field generated by this guy, it's actually slicing through the secondary coil. Even though the coils aren't touching, I can bring them very close together, right? But if this fist is generating a magnetic field, it's going up, down, which means bigger, smaller, magnetic field strength, right? And then I physically move it closer, then those magnetic field lines are going to cut into the secondary coil. And it's the cutting, getting bigger and smaller of the magnetic field, cutting across, for lack of a better word, the coil lines in the secondary coil that then generates voltage V2 even when they're not touching. So the voltage is generated here as a result of this magnetic field here that's slicing through the secondary coil. Bottom line there. Okay? So then what we say is that the equation of interest here is V2 is proportional to something, instead of L for self-inductance, we say it's proportional to the mutual inductance, the mutual induction between the two coils, times di1 dt. So this is a really fascinating equation to me. What it basically means is I can build a coil of wire, I can connect it to a source, so I have current circulating in a sinusoidal up-down fashion. I can build a secondary coil, I can move it close to, but not touching the first coil. And just from their physical proximity, there's something called a mutual inductance. We label it M. It's also going to be in henries, so we'll call that in henries. Right? And the voltage induced in the secondary coil due to the current flowing in the first coil is equal to this quantity called the mutual inductance times the derivative of the current flowing in the other coil. Think about it, that makes sense, because what's happening here is this is generating a magnetic field, so the derivative of this current is basically telling me how much the magnetic field is changing over here. The mutual inductance is going to be proportional to how close these coils are together. So if I build the coils this far apart, the mutual inductance is going to be low. If I build them this far apart, it's going to be higher. If I build them this far apart, it's going to be much higher. And let's say I have a single tube like this, and I wind the first coil on this, and then I take the second coil and I wind it almost right on top. Of course, the wires are insulated, so they're not short-circuited. But let's say they're wound on the exact same coil, on the exact same tube. Then in that case, the mutual inductance would be even higher because the magnetic field would be very, very close to the secondary coil. So the secondary voltage that's generated here is equal to the mutual inductance times di dt, but it's the current in the first. I guess I should put this as I sub 1. I sub 1 here. Sub 1. And so you have a voltage drop and there'll be a current circulating through. If I put a load here, there would be a current circulating through that as a result of this guy. So you can see the symmetry in the two equations. Self-inductance is basically when you have voltage generated as in the same coil where the current is flowing through it because the magnetic field lines are cutting through the same coil that the current's flowing in. And we call that parameter of the constant of proportionality the inductance, or the self-inductance. And then we have the mutual inductance, which basically means that you have a parameter measured in henries also, or millihenries or whatever, that measures how tightly these two coils are coupled together, we call it, in terms of their magnetic field. And the form of the equations are exactly the same. All right? Now the interesting thing about this, this is more or less what a transformer looks like. Now, I'm not going to draw it here, but we will when we talk about transformers. You can have iron here, that kind of a solid core of iron to kind of make the magnetic field stronger and those kinds of things, and concentrated. I'll talk a lot more about that later. But you certainly don't need an iron core in order to make this mutual inductance happen. It just needs physical proximity of the two coils close together. Now the interesting thing here is I've drawn it with two coils, and so you might say, okay, that makes sense, I understand that. But you can actually have some pretty wacky circuit configurations that involve more than two coils. We're not going to solve any problems here, but I'll just draw a few examples to show you what kind of things can happen. And so that's generally where we're going, and the math can get quite complicated because you have differential equations with these derivatives running around everywhere in your calculations. So let's just take a couple of examples of mutual inductance. So we'll say mutual inductance circuits. All right, the simplest one obviously is with two coils, and we've already drawn kind of a general one there. This is not an exhaustive list. This is just kind of some stuff I'm going to sketch out for you just to kind of show you a couple of examples. You could have a voltage source with a resistor, right? And then you could have some coil here, and then you could have some coil here, right, like this. And then you could have in parallel with that another resistor, let's say. So for instance, a circuit that you might see would be that this resistance doesn't matter. You could say 1 ohm. You could say 1 ohm. You could say this is like 2 millihenries. And you could say this is like 3 millihenries. So you see when I write the numbers above the coil, that is the self-inductance L of that coil, just like it always is. But if these two coils are physically close together, what you see on a circuit is you see an arrow, a double-headed arrow that's pointing, hey, look at this one, look at this one. I'm pointing to both of them. And you might see 1 millihenry in between them like that. So what this means is that the self-inductance of this coil is 2 millihenries. The self-inductance of this coil is 3 millihenries. but the mutual inductance between the two is 1 millihenry. So what that means is this coil has some inductance, this coil has some inductance. I didn't arrange this like a transformer. This is kind of written like a transformer you'll see later when they're kind of up against each other. This is not drawn like a transformer. These are in different branches. It's like a mesh here, a mesh here. These are not really kind of like lined up. They're kind of like this or whatever. But there's still a mutual inductance between them. Why? Because this coil is going to have some current going through it. And when that current happens and it's going up and down sinusoidally, then what's going to happen is it's going to generate a magnetic field, which is going to get bigger and smaller. Now this coil happens to be nearby, maybe not really close, but it's nearby, and it's close enough so that when the magnetic field changes here, it cuts through, the magnetic field lines cut through this coil and induce a voltage over here, just like we drew here. But there will be a voltage induced here because of that, and you denote how much coupling is involved between these magnetic fields with a mutual inductance M, right? You can have other crazy arrangements. We're not going to go crazy and talk about too many of them here, but we'll just draw a couple little examples. We can have a coil here. I can have a resistor here, and I can have another coil here, and then I can have a resistor on this side. So I might say, for instance, that this resistor is 10 ohms, and I might say that this is 5 ohms, and I might say that this is 2 millihenries, and I might say that this is 10 millihenries. So obviously these are the self-inductances, the inductances of the values of those coils, but then I can draw a double-headed arrow between here, and I might say this is 6 millihenries. Now you see, this one even looks weirder because this is, the way I've drawn it schematically is this coil is very far away from this one. But you got to remember, this is just a schematic. This is just how we draw it on paper. When I build this circuit, I can, as long as they're connected properly, I have freedom to put these coils right next to each other. Maybe I build a phone or something, and I have a coil of wire for the antenna assembly, and then I have another coil of wire, an inductor that has something to do with a filter or some kind of other part of the amplifier circuit that's totally separate and different from the antenna part. So they have the antenna thing going here, like this part of the circuit, and I have some other inductor that's part of some other amplifier circuit over somewhere else. But when I actually physically build the device, I just happen to put those two together just because it fits in the case a little bit better. Maybe if I put the coils kind of close together. So even though they're drawn like this on paper, it doesn't mean that the coil has to be far away. I could pull this thing close, and as long as I have the nodes and everything proper, I can certainly put that coil physically close. And when I put them physically close to one another, the magnetic field from this guy is going to cut through this guy. It's going to induce a voltage here, which is going to be represented as a mutual inductance. So the mutual inductance is basically how coupled the two coils are together. And then I'll just show you one more really quickly, just because I find it kind of interesting, but we'll just do it like this. Let's say you have a resistor, you have an inductor, you have another inductor in this kind of node, or this kind of mesh down here. And let's say you have another guy here and a resistor over here. This is kind of a crazy example, but let's just say you had 5 ohms for that resistor, you had 6 ohms for this guy, and we said, now notice that all of these inductances, we wrote them down in henries, right? And of course, a lot of times you're probably used to seeing things written down in terms of impedances. Remember, J omega L is the impedance, where L is the value of the inductance. So when I draw a circuit, I can just write, a lot of times it'll be given to you in terms of the impedance. So this could be J2 ohms. This could be, let's say, J10 ohms. And this could be J100 ohms. But then you might see something crazy like this. You might see an arrow between this, and that mutual inductance is J70 ohms, right? And then you might see an arrow between this one all the way over to the other coil, physically far away, and they might say J12 ohms. And then you might see a mutual inductance between this coil and this coil of J16 ohms. I'm making the numbers up, but you get the point. Every coil in your circuit is going to have an inductance value, or you can write it in terms of an impedance, right? And every coil is going to be sitting some distance away from every other coil. So in real life, there's always a mutual inductance between coils. But it's just that the farther I put them away, the lower that mutual inductance is. The closer I put them, if I start winding them on top of each other, it's going to have a really high mutual inductance. And the closer they are, they're going to have higher and higher. You can have these weird configurations like this. So we are going to learn how to solve problems that kind of go in this direction. But I will tell you, right off the bat that problems like this are very difficult to solve because the system of equations gets difficult when you have all of the meshes involved, and then you have all the mutual inductances, which end up adding terms to all of the equations, so that the equations can be a little difficult to solve there as well. So these equations can get quite difficult to solve mathematically. They're all doable, of course, once you know how to write them, and we are going to get practice with that. So in this lesson, we introduced the concept of, or reviewed the concept of self-inductance. It's a coil of N terms with a known equation we've been using all the time. LD IDT, that's the induced voltage there. The concept of mutual inductance is when the coils come together, how much voltage in that secondary coil is going to be generated due to the changing current in the first coil, all right? And then I just kind of gave you a little potpourri of some weird circuits that we're going to end up getting into later on down the road. Now, we're going to close for now. In the next lesson, what we'll do is we will get an overview, again, just an overview of the concept of a transformer and kind of dive a little bit more detail into that. And then as the rest of the course proceeds, we are going to dive into great detail, much more detail than what we've gotten into here, talking about the physics, about what happens, deriving a lot more equations, and solving problems. Learn anything at mathandscience.com.